There we go. Okay. All right. Let's jump in. We're gonna do kind of a partial review. So this is stuff we need the soonest. So we're gonna cover a lot of this stuff. I know you guys saw this in your most recent Comp 130 class, but some of us need a little refresher, and I'm gonna dig a little deeper around the corners. So this is an opportunity to maybe pick up a few little insights that you missed the first time around. I know it'll be a little bit tiring. We're only going to do one lecture like this, really, and then we're going to start building stuff. There are kind of two other parts to this lecture. I call them 2B and 2C. You can pull down those PowerPoints or watch some videos from, frankly, a year or two ago, and they're going to go over like all of the stuff you learned. But every time I try to fit that into this class, it's just way too much. So this is 2A is just sort of like pulling out the review stuff we need the most. And then other stuff, if you're feeling really rusty, go back and look at that, or possibly look at W3 schools or maybe the Program IZ content and see if you can do some review there. But many of you will probably be okay. And so we'll just kind of spend some time on this one, and then we'll be able to start doing some more entertaining stuff. Maybe that's new stuff you guys haven't seen. So reminders as usual. So we had our lab 1, lab 2 is tonight. It's a little tricky, but we'll go over it at the end of the lecture to give you some pointers on it. You can certainly get it done the easier way pretty quickly. The hardest, most efficient way is a little trickier, but also fun to go after. And then of course we have our homework 1 is out. We talked about that briefly last time, so I won't go over that again, but you should have everything you need to kind of implement that. If you're rusty on C++ classes, we will review that on Tuesday next week. So that'll kind of give you maybe a review if you need some of that. But otherwise, you should be able to jump in on that stuff. And you can wait on quiz 1. Although if you haven't taken my class in a while, just remember, you can have a total 0 on quiz 1 and come back and replace that with your second or third try. So if you kind of want to size up, do I know this stuff from last semester or not from C++, you can kind of go take your quiz 1 quiz now, and then you should be okay. So Kevin, are you here? Yes. Okay. That's okay. I just want to make sure I'm not allowed to let anybody in if you're not here. So, so that's kind of a new rule. Okay. So that's that stuff. So please keep that stuff in mind. Also, if you wanted to do this, I've put a bunch of your names in there. Just check your inbox. If you're not seeing something, let me know, and I'll go back and resend the invitation. But I've seen people join, so I know some people are getting it. So no rush on that. Just so you're clear, like we're going to use the online free Program IZ thing and Replit in a pretty quick way. But where we want to go, especially for our bigger projects, is we want to be able to write multiple files, as part of our program that gets compiled. So we're either going to need to do that in VS Code or Replit or this Program IZ Pro. So Pro is a little more feature rich than the stuff we're using on our practice problems. So I know it's a little confusing, the difference between those two. So no rush on Pro, but if you want it, go for that. Also, you've got your VS Code and your Replit options there. So team project, I've thought about this. And I think I want to kind of change it up a little bit. Lab 4 was going to be the beginning of a collaborative thing, and it was kind of a little bit smaller team, smaller project, but I think I want us all to act like a software company. So kind of looked around at some of the game ideas that are out there. And so I think we want to try Risk. So what we're going to try to do is we're going to attack this game as a text-based game. We're going to basically divide up into small teams where every team is going to have an object-oriented portion of the game that they need to develop. And so we will get to this roughly next Thursday in lab. It'll be our first opportunity to sit down and discuss, okay, how are we going to break this up? Who's going to be on what teams? It's going to be kind of experimental, but hopefully fun for you. It's going to stretch out over the whole semester. And so like every fourth lab, we'll sort of, form our software company, and we'll just talk about where we are, who's made progress on their individual parts of the game. And as you can imagine, they're not going to always fit together properly. And that's what happens out in real life. So hopefully this will bring out some real life software development experience for you. And at the end of it, we should all have a playable game. And it's going to be a text-based game, but to be sure, like just because we're drawing it in text doesn't mean we couldn't upgrade it at some point with a graphics library and turn it into a full scale game. So hopefully you kind of feel like this is more than just a toy, and everybody will get a chance to work on some portion of it as we go along. So I don't think it's going to be a really complicated game, especially considering the number of people that we have here. We just got to break it down into reasonable objects. So please do, if you get a chance, take a look at the rules. And for those of you who are serious risk aficionados, if you have a different set of rules that you'd rather that we be following, I can defer to your judgment on that stuff. But I just sort of grabbed the classic set of rules out there so you can kind of read about them. And I'll be kind of recommending an object-oriented structure to you, but we'll talk about this in lab next Thursday. And hopefully you can kind of begin to group up and start thinking about your portion of this thing. So should be a low stress thing. And it should be a fun thing where maybe you come up with some ideas where you want to add something to the game that maybe is not even part of this classic game. So I'm curious to see how it comes out. It can be a little bit messy, but I think it's a fun and important thing. And hopefully we'll get to know each other a little better in the process. So any questions on how we might be approaching this thing or how you want to get ready for it? Comments from anybody?
It's not a picture risk, correct?
No, it's not. That is a chat GPT. Make me a board game that isn't Risk. So I guess
I was like, boy, it's changed a lot.
yeah, no, it's funny because when you tell, because if you tell AI to generate a picture of a Hasbro board game, it will refuse to do so appropriately because it's against its policies. But if you couch the terminology well enough, it's like I need a board game about territories where there's capturing and strategy, and it's what it's really probably thinking is Settlers of Catan with that picture, So anyway, just inspiration for us, and maybe we'll find a way to make it look, approaching some of that coolness. So let's though dive into our review and bear with me on this stuff. There's more practice problems than you probably can or want to do during my presentation, but I'll lay them out for you. And if you see one where you're like, oh, I really need to review this, kind of make a note to yourself or maybe dive in and sort of zoom into that particular one. I'll try to throw out some extra stuff you may not have known as we go through some of these things. But the idea is, we don't have to come back and review this stuff too much. We want to build on top of it and just start adding new knowledge to our foundation. So we're going to cover, what is main, right? Just go back to something we kind of know. Cout, of course. What is a namespace? When should you use it? We're going to talk about arrays again, and we're going to refer to this as a C array. And this is the old-fashioned, very low-level array that is very close to assembly language. So for those of you who are or already have taken Comp 160, you should know that an array in C or C++ is almost exactly a direct mapping to memory in the computer. So it's about as low level as you can get unless you're going to write assembly language. So we're going to go back and talk about that a little bit. Well, let's talk about a strange little collection of characters called a const char string. So this is rather confusing to people when we get so used to using the string data type. So const char string is something special. We'll talk about what that is. Remind ourselves how to use quotes and escaped characters. And then we'll remind ourselves about the string container. So we never really called it a container in previous classes, but C++ provides a whole bunch of containers. Vector is another kind of container that you all should be somewhat familiar with. And there's a string container. There's also an array container we're going to learn about, not to be confused with the old-fashioned array. So we're going to study lots and lots of containers. So we'll start referring to string as a container, even though we maybe had just thought of it as another data type like int and char and stuff like that. We'll do a couple quick reviews on for loops and then point out a few new features you might have not have known about it. remind ourselves about pre and post increment, because that's really important. And we're going to use the time library to measure performance and just demonstrate the passage of time. So we'll review that along with RAND and SRAND and our good old ternary operator, which is just really handy for kind of compressing if else into a very small space. Okay. And then our CN has some tricks up its sleeve that we really didn't spend a lot of time on in a previous class. So we'll be using that a lot more for some tricky processing of inputs from our users for our game input over the semester. So we'll kind of go over that briefly. So you don't have to master them all today, but these would be the kinds of things as you come out of this class, you should feel very comfortable, at least on these 10 things. Now, there are more practice problems out there for parts B and C of this lecture that I'm not going to go over live. So you can kind of scan them in Canvas in the modules and just kind of go, hey, I think I know that, or uh-oh, I better come back to that soon. So there's a lot of them I know, like this is kind of today, right? So all of this stuff is kind of what we're doing today. There's about 10 of these things that we're going to go through. And then the other stuff that we won't go through is kind of still there, and you can kind of click in and review briefly. Most of those links are unfortunately still in Replit, but you can see the code and copy paste it over to your favorite system if you want to work with it. But at least you can compare, the before and the after and kind of see, oh yeah, I can see how you solve that particular problem. Okay. So I know it's a lot, but at least you got that to come back to. And it's sort of a compressed kind of representation of everything we should have covered. Not exactly everything, but most of the stuff we covered in Comp 130. Okay. Any questions on that? Okay. All right. So let's dive in and talk about main. So one of the things we did not really use in main were its arguments. So main is actually a function just like any function that we could write. And it has these two mysterious arguments called int argc and char star argv. And you can see that argv is an array. Anybody know what values get stored in the argv array based on the declaration? Any guesses? Exactly. Pointers. Yeah, that's the first and foremost thing. Pointers. So each of those positions in that argv, we don't know how big it is, right? That's actually told to us by the argc. So argc there tells us how many pointers are in the argv array. Any guesses what those pointers point to? Character. So a character. Yeah, you're probably overthinking the problem. So they point to a character which is followed by another character and which is followed by another character. So essentially this argv is a list of words, and those words represent in order the name of this program as far as the operating system is concerned, and any command line arguments that somebody might have typed in after the name of the program. So for those of us who kind of grew up on Replit and other things, we might be like, wait, I thought we just hit the run button. Well, yes, but what's going on in Linux or whatever the operating system is with our code is it's executing our program as a compiled executable named file on the file system. And then maybe there are extra arguments like some data that we want to read in from a file, etc. So in the old days, those things all had to be typed at the keyboard manually. We now have a run button, but still main is going to give us that information, and we can sneak a peek at what's going on in the background or in the cloud by having access to these particular items. So if we want to look at the code for this, we can do that. Really, all we got to do is sort of add a little bit of cout magic to our main to sort of figure out or hack around and see what's going on. What is the name of this program that's actually being run? Okay, so we'll come back to that in a second. You're welcome to kind of click into these things if you want. I'll have some program IZ links here briefly that will actually work for you. Although I thought actually I had this. I wonder if I actually uploaded the wrong thing. Well, let's just continue here and see how far we can get. So here's our cout, standard std double colon. That's what we call our scope resolution modifier. Std tells us where to go find cout. it's not in a library. It's actually kind of in a little subgroup inside of that IOStream library. And if we don't specify what our namespace is, as many of you already know, we have to say it over and over and over again every time we try to use a command from that IOStream library. Now, out in the professional world, that's what people do. They just kind of get used to typing std : a lot. We have been cheating in our classes by using the namespace above main, and that is somewhat frowned upon if you go work for Google or anywhere else like that, right? So notice we don't have using namespace std above main there. So we have to actually specify that stuff everywhere. Okay, so let's come back to this argc and argv thing real quick here, right? So argc, how many command line arguments, including the name of the executable file that represents our compiled code, okay? And then argv is the array where we pull those names out, okay? So if we were executing our program called doit.exe, from the Linux command line, we would just type doit.exe and suddenly it would run, and maybe it would type hello world and it would be done in a matter of seconds, right? So that's one argument in position 0 of our argv. So position 0 of argv is the name of the compiled executable program. And you might think, oh, isn't it called main, or isn't it called a.out? Like, what is it called? Well, different operating systems or different systems like ProgramIZ might compile it and call it something different, right? So we don't really know unless we can take a peek at the file system or just sort of ask the argv what's in position 0. Now, if we had written a program that kind of slurps up a data file, and we actually are specifying that on the command line argument in Linux, that's going to be in the position 1 of our argv array, okay? So a lot of tools that are written as executable programs actually work this way. They kind of specify the file name on the command line, and we can write code to kind of figure out what that is. We still got to open the file ourselves with our own code, but we do it via the argv array that comes in this main function prototype here. Okay, so we got 2 arguments in that case, position 0 and position 1, and then it kind of goes on and on. So I could specify an input file or an output file or input numbers, all sorts of things I might do on that command line argument there. And so all those things come in as a pointer to a string, right? So those are all going to come in as strings, okay? Notice I put my quotes around them there to kind of emphasize that. So let's just take a look at this real quick. So the idea here is, and again, you don't have to do all these things, but you can either click in to ProgramIZ, you don't have to log in or have an account, or if you've got Replit going on, you can kind of click into that. But I'm just going to kind of show you the code in action here so you can kind of see what it looks like. So if we want, assuming that we have our namespace not used, right? So we have to say std. We can say this program has argc arguments, including the program name, right? So that's our first step, right? And if I print out argv of 0, it's going to print out that bag of characters that are pointed to by position 0. Now you might ask yourself, well, if it's a char pointer, that means it's just pointing to the first character. How does it know where to stop? Well, cout is going to stop when it runs into a \0. So all of these kind of command line arguments are padded with a backstop, a \0 character, and cout is looking for that character to know how many characters it should print. So it's going to keep going and keep going until it bumps into that in the end of that position 0 section, and that's what gets printed out for. So that would be our program name, and if we ran this thing, we would actually see that thing get printed out. Now, the interesting thing about ProgramIZ is if we run this out, and this is, you can kind of be a little bit of a hacker here, you'll see, oh, interesting, my program is called main.o, that's the executable name of my compiled version. And they're a little sneaky. They kind of put it over in the temp folder in Linux. And now we know 2 things, right? We know the name of it and we know where the compiler for Program IZ is actually storing this executable on some cloud-based machine somewhere. Okay, so all that is coming from my arg0. Okay, now we don't have any other arguments on this because we only have one argument, and that is our program name. But in other scenarios, we might have lots and lots of arguments. Okay, so we won't see much of this semester because everything we're going to do, we're going to kind of know already what files we want to open. But very, very often out in the real world, we're going to be using that argc and that argv to grab those command line arguments right off the command line. Okay. So if you've ever used any Linux commands where you say something -v-w file name -x, well, all of those dashes and all those things are coming into that program through the argv array. Okay, so a little extra sauce for you. We won't see too much of that during the semester, but it is an important thing to actually know about. Okay. So let's go back to namespace real quick. So I point this out because, you know, if I sent you out into the real world and you said, well, my professor said that I should use this, they would think I'm probably a terrible professor. So we often put the std : in there out in the real world because when you establish a namespace, it affects everybody whose code is compiled into that executable. So let's say we're all working on a separate .cpp file, not just a main.cpp, and we're going to glue them all together like in our Risk game. If one of us sets the std in the wrong place, it can affect all of us. So when we're working all by ourselves, it doesn't really matter what namespace we use. But when we work in a large professional team, we tend to be, you know, more verbose and just put it here at the individual command level. It's tedious because we got to type it 1,000 times, but it is safer than kind of doing it that way. Okay, so totally fine when you're working by yourself, but out in the real world, just heads up, you'll probably see this is how we do things here. Never, never, never use the using namespace std thing. Okay, so it's okay in this class, but we'll actually kind of when we send you out in the world, we'll try to have you not do that, right? So here we have our namespace, simplifies our code, of course. That's how we've been doing things all along. And remember that, and we'll talk about this here in a minute, we can do things like escaping a quote, right? So if I want to say the name of this program is \quote is just a way of saying, hey, that's just a part of my message, right? The actual final quote is over here. Okay, so it's very common to use a backslash when I want a quote inside of sort of cosmetic description of some name or something. Same kind of thing with a single quote, backslash single quote, etc. So we'll do a little reminder about those escape sequences here in a bit, but that's the main difference between that. Okay, so let's talk about arrays. Okay, so again, there is a container which you've never probably seen before, kind of like vector, that is simpler than a vector. It's called a container array. But old-fashioned C arrays or C++ arrays are much, much more low level than that. And we've seen it, so it's not really a big surprise. They're super powerful, and of course, they can hold pointers to other things, instances of classes, all sorts of things. So pointers or arrays are super powerful, and they're kind of still the workhorse of highly optimized code. So we can't have arrays of references, right, or arrays of functions. That really is not supported. We can have arrays of pointers to functions, and we will see that in this class. But there are only a few things that arrays can't hold, and references are one of them, right? And if you don't remember reference, don't worry about that. We'll come back and talk about that. So there's our array, right? We got a set of dimensions, so we can't do anything like that, but we can leave the dimension out and let our initialization packet kind of specify the dimension for us. So that's totally fine, okay? Now, here's where I'm sure folks are probably going to be a little fuzzy. This is a whole different kind of way to allocate stuff. So here we're saying, give me 5 integers dynamically. That's the key. When you see new, we're doing something on the fly and we have to clean up our mess, right? If we're doing it up here, C++ is going to clean up our mess for us, okay? So this is dynamic memory allocation. We'll be doing a lot of that this semester, and we'll be reviewing that here in a little bit. But it is got a lot to do with pointers and a lot to do with new and delete and allocation. So that's something that we'll want to kind of come over and review. Okay. But that is kind of the power of our C array. Why I can't quite get my menu up there, but that's all right. I'll just kind of move on. Now, string, okay, C strings. So a C string is this. It's just an array of characters. Now, if I don't put a \n at the end of it, I can't feed it to the cout command because the cout command doesn't really know how far to go to print it, okay? This actually creates an array dynamically of 5 characters. And now I can go fill that in with maybe 5 characters that are ending with a \n. Now, if I do something like this, I'm actually creating something very similar, right? I'm creating an array, right? And I'm filling it up with all these characters, right? But notice that there's no \0 character in there. It's not the end of the world, but if you were to feed this to cout, it would not know where to stop. It would keep printing and printing and printing and printing and printing and maybe print garbage on the screen, or it might refuse to print it altogether. Okay. So normally we can't print something like this out using cout unless we give it a little bumper at the end. And of course that bumper takes up a little extra space. That is a single \0 is a single character. It's called the null character. And usually we use it to signal the end of some sequence of something in code. Okay. Now, sometimes we just refer to some string in our code and try to shove that into something on the fly, right? And that's a little bit different. We'll come back and talk about that one here in just a little bit, okay? But otherwise, these are just 2 different ways to build an array. This is a dynamically allocated array, and this is an array that's created at compile time. So this gets created at runtime when we run our program. This gets created when we compile our program, okay? That's why we call this one dynamic, okay? So we'll see that in code. Reminders about quotes, single quotes for the char data type, okay? And double quotes for a string, okay? So notice that \0 and \n is a single character. And I know some of you are probably like, wait, what? Right? But \ just tells the compiler, hey, don't treat that like a 0. Treat it like that special null ASCII character. \n says treat it like that special carriage return character. You might think, who came up with these? Well, they've been around for a very, very, very long time. They don't make a lot of sense. We just got to kind of memorize what they mean. But they are one character and they deserve a single quote on either side. If we were to say char C3 equals double quote C, we would get a compiler error because the compiler is going to say, I can't fit a string into a character space. Okay. So that is a string. Okay. Right. We cannot put that into a single character. Okay. And if we could, it would probably be some kind of corrupted memory, okay? So whenever we see double quotes, just think word. I'm putting a word in there of size 1 or 2 or 5 or 10,000, right? It really does not matter, okay? So let's take a look at these 2 pieces of code here. So E4 equals 1, 2, 3, 4, okay? So this is actually going to try to pack in an extra \0 here, right? And that's going to try to take up 5 spaces. I believe I've got that right. Somebody may want to check that out in code and see if that creates a compiler error. If anybody's doing that, feel free to test that. Also, this is a problem over here because this is a single character. We're trying to put it into an array of 5 things, okay? So these are just annoying little things that might pop up. Don't worry if you don't have to memorize all this stuff, but sort of just, might jog your memory if you got some kind of a nasty bug you're kind of trying to figure out down the line, okay? So again, just about escape characters real quick. There are all sorts of interesting things that we can do with these special characters. \n is just a way of saying, hey, don't treat this like the end of something. It's just a character inside of my quoted string. Or don't treat this like the end of my sentence, just treat it as something in the middle of a sentence, like my name is Jeff, okay? So those escapes or backslashes are powerful things. This is actually not widely known. You can, in the middle of your code, say backslash, hit enter, and C++ will accept that, right? That is one way of breaking a coded string across multiple lines. And there are not a lot of times you need to do that, but sometimes it's really helpful to do that. Seems somewhat magical when you actually do it, okay? So a practice problem is, this is a good one actually. So let's just think about this for a second. If you had to write a function that put a particular character at the beginning and the end of some array that is pointed to by this S pointer, right? So S is a pointer, right? So we're going to be given some pointer to some string and we want to put something at the beginning and the end of that, assuming that we have enough memory to do that, okay? So in other words, if I gave you wow and a quote, you would actually have to sort of put a quote at either, or that character at the front and the back of that. So let's look at the code for actually doing that, okay? So I'm going to kind of quick go to the solution here so you guys who are working on it can do it, right? So if we're just printing it out, right? We're not returning it, sorry. We're just printing it out. So cout, the character followed by the string followed by the character. That's all we're really trying to do, right? That's pretty straightforward, but there's a gotcha here I want to show you, right? So here we say, hey, there's my array of characters, and I want you to go ahead and put the backslash character before, or sorry, put the single quote character, backslash single quote, right? That's not a double quote. That's a single quote, backslash single quote, another single quote. Not tricky. Put that on either side, right here and here, of my string. Name is an array of characters, but notice how we declared it here a char star. That's all an array really is. An array is a pointer to the first item in a collection of characters. So we can declare this as a pointer, and C++ should be relatively okay with that, okay? Now, if we do this, that works, right? But if we try to put a string in here, we're going to get a warning from the compiler. It's going to say, hey, that thing is not a char star. It's actually a const char star. So this is constant because it's not allowed to be changed. This function is not allowed to change something that we put in quotes like that. That is a literal string and is not changeable by our program. So many of us get confused because we write this function and immediately we find out we can use it here and here, but we can't use it here. And if I think, oh, I'll just put the word const in here, then it starts complaining about these two uses. So you're like, well, how do I get this thing to work? And so the solution for this one is what we call overloading. And some of you will remember that from before. We actually have to have two versions of the function. They essentially do the same thing, but this one gets called when we call it this way, right? Right? So if we have that, this second version, this overloaded version, that handles this kind of usage, and this other one handles this kind of usage, okay? So this is the kind of slightly crazy stuff we run into in advanced C++. It's like, oh gosh, all this const stuff can make me crazy. Yes?
So, creating like overloading a certain function works for other things apart from just these two instances, right? Or these.
Yeah. So let's say you had other overloaded things with the exact same name, but a different function signature. Then the usage down below identifies which function is going to get called. Yeah. I don't know if that answers your question, but that's generally why we overload things. Yeah. Yep. And you know what? It's possible to kind of be optimal and find a way to have this function call this function, right? So you don't have to necessarily duplicate all the code, but we have to satisfy the, apples and apples, right? This is a const char string, so that has to be a const char argument. Okay. So this is a tricky one, so I will always warn you about this, but you might run into this in your travels in C++ where you're like, why is this silly thing not working? I hate const, right? It kind of drives you crazy sometimes. So overloading that thing for these literals might be an important thing, okay? Okay, so that's the old school, if you will. Like all of those collections of characters, like many of you just like, oh my gosh, I wish we could just work with the string. And the good news is most of the time we will. When I started out in C++ and C, there was no string container. In fact, before 2011, believe it or not, there really wasn't a string container. So we have this now, and this is really the most modern way to work with collections of characters. So we've all done this before. We say string, my name equals Jeff. But what we might not have known in our beginning coding class is that string isn't really a fundamental data type, right? It looks like it. It looks like int, char, whatever, and we've sort of treated it that way. And it kind of works fine, like we assigned a value to a variable, but in reality, it's an instance of a class. So when we say string my name equal Jeff, we're creating an instance of the string class in the variable Jeff. And the equals Jeff part is actually what we call syntactic sugar for calling the constructor. So C++ has this thing most languages do called syntactic sugar for humans. It's like, oh, you humans, you just like working with things that look like math. So we'll let you put an equal sign in there, but what you're really doing is calling the constructor for the string class and feeding it the word Jeff, okay? So it turns out all of those nice methods that we get from string like dot size and dot c underscore str to get the raw character information back. Those are all just methods inside of this string class, okay? And the equals thing is just a tricky way of calling the constructor, okay? So I'm going to standardize on dot size, even though it's equivalent to dot length. And I would suggest you do too, because every container supports dot size, but only a few containers support dot length. So if you want to relax your brain a little bit this semester, you can kind of memorize one less thing and just focus on the dot size. But you're welcome to use the dot length if you want to, okay? So this one is really just about copying information from our argv into a string variable. And that, fortunately, is something that we're allowed to do. So I'll just show you the code here, but again, feel free to jump into the actual code if you want to. So here we are creating an instance of the string class, and its constructor is receiving an argument. So you might be thinking, well, wait a minute, how does that work? Well, probably the string class has overloaded constructors for all the different kinds of data types that we want to feed to it. Old type string, const char string, all that overloading stuff is kind of handled. And it just sort of works nicely for us, okay? So we could have done this, right? I could have said string prog name parentheses. Remember, that's how we call a constructor. Right, so what we're really saying is construct an instance of the string class called prog name and feed the constructor a name, right? Some information from my command line. So argv0 is, of course, our program name. So now we have a string variable. It's not really a variable so much. It's kind of an instance of a class, but we call it a variable. And I kind of like to treat it like a variable. And now we can just print that thing out, okay? And that's really, of course, the modern way to work with this information, okay? Because we get all those nice methods that come along with it. So we're going to spend a lot of time in this class building our own classes, creating our own methods, and working with our own constructors. So these familiar patterns will help us kind of get started. But we're going to, as you may recall, we did this a little bit in Comp 130. We're going to do that a lot more in this class, of course, okay? So a little refresher on creating instances of classes. Okay, a couple of secrets about the for function, and I'll try not to dazzle you with too much of this stuff, but the for function is way more powerful than we probably realize, right? So of course we set the initial condition, we test for while we're gonna, under what condition we continue, and then we want to change x, okay? But you can do a lot of crazy things with this thing that you probably didn't realize, right? Of course, we put our code inside of there, and our x equals x plus 1 happens at the end of that code execution. Okay, so most of us have had enough practice with that. But the key thing to remember is that your variable goes away after the end of the curly brace. So many of us probably remember that. So you can't use the index variable outside of the for loop. But some things you can do is you can separate things with commas here. So you can create multiple tracking index variables in the first part of your for loop. And then you can also separate commands inside of here with a comma as well. It's not super common, but you can do some super tricky for loop stuff that way. Very compressed, very optimized code, okay? So it's a lot more powerful than maybe we might think, okay? And you can leave stuff completely out, right? So you really don't even need to have anything in here at all, right? So if these variables exist outside of the for loop, then we can just leave this section blank and just have our semicolon in there, okay? So it's a very flexible kind of a tool, okay? And we can even move the incrementing, right, into our curly braces, and now we have a while loop, right? I mean, we might as well have just used a while loop in this particular case, okay? But what the for loop is, of course, really good at is it's going to create these variables now, and then they will go away after that last curly brace. And hopefully remember we talk about this as being scope, right? This is a neighborhood where related things happen and they go away after we're done executing that for loop, okay? So super powerful, a little bit strange sometimes, but you get used to it for a lot of things. So here is a classic thing that we might want to do. We might want to increment something, but we want to know what the value of it is after the for loop. So how do we do that, right? Usually if we kind of put it in the for loop the normal way, we can't see what the value is after. So it's really easy to actually sort of make a hybrid for loop where we declare the value before we enter the for loop and just leave our initialization block blank. So now, of course, the I exists in this neighborhood, right? And so we can, sorry, I don't have my main thing there. Sorry, let me clear that up and do that again. So the I exists in this neighborhood. So of course we can check and see what it is after the fact, okay? So that's perfectly fine. And so this might confuse you a little bit, but all we're really doing here is sort of resetting the I to 0. We're not declaring the I, right? Notice there's no data type here, okay? So that is perfectly legal, but kind of tricky code. You kind of go, oh, I guess I must have existed already, right? So just so you know, you can do that. It's okay to refer, of course, to any variables out here. You don't have to declare them in there. And that's allowing you to refer to this outside of the scope of this set of curly braces, okay? So scope is so important for obviously what's going on in your code. Okay, little subtle things about our double increment and double decrement. So we call it pre and post. So these are like little puzzles. We don't do it too much, but you might have wondered why you do it before and why you do it after. So in this case, A gets the value of 5, and then B gets incremented, okay? So it's like we move the 5 over there, and then we add 1 to B. That all happens in one line of code. So now this is a 5, and this is a 6. So here I'm saying, hey, copy the B over, but increment it before. So that means if B was 6, now C is a 7. Okay? So C is a 7 and B is a 7. Okay? So understanding the difference between these things will be important in certain situations, okay? A lot of times we just sort of do these things on separate lines, but when you pile it all into one line there, it can have some unintended consequences. So one of the more advanced things you want to know about or remember is about pre and post increments. And of course, same for minus minus, right? So it has the same kind of effect. Okay? So you'll probably see some quiz questions on that. Now, for a for loop, people often ask, which one should I do? Should I do it before or should I do it after? Well, it really doesn't matter in that case because that increment happens at the bottom of our loop after everything else has happened. So it's not going to really have an effect. So some people will do pre-increment and some people will do post. It really doesn't matter in that case. Okay. But it is an important thing to know exists. We'll kind of run into it from time to time. Okay. And for those of you who took algorithms with me or might be taking algorithms, there's some pretty tricky algorithms code where they use this pre and post thing to make super, super optimal solutions to big, big problems. So, okay. So we won't go through this one, but this is essentially just, testing your understanding of that, right? Seeing if you can predict or change the value or the order so that you get a particular value out of there, okay? So we've declared the I outside of the for loop. We're only doing the increment at the bottom, and you could do it, pre or post. Notice that doing it post gives me normal behavior of a for loop. It says print out I and then increment it after I've printed it out, okay? So let's just pause on that because that is kind of important. So it says see out I, which starts out as 0. So we'll see the 0 first. We get an increment, we loop around, and then we print it out again, and then increment. So when we're done down here, we will get one extra increment that we'll never see in our printed output. This can lead to some pretty surprising bugs if you don't really understand that that's what's going on. You'd be like, wait, I should be 100, right? And it's like, okay, well, it's, it's 101, right? It's a one off of what I thought it would be. And it's probably because of something like that, okay? Assuming we declare this outside of there, okay? So just be aware of it. We won't run into it that much, but it can be kind of surprising, okay? Okay, time from the CTime library. That's a pound include for CTime. A lot of times, things like Replit and a program IZ will have already loaded the time library, but we should arguably be loading that all the time. So here's our pound include CTime. And so the way we use that is we sort of give it a null PTR. That's kind of like a 0. You could probably also put a 0 in there and it'll work. But that's going to give us the number of seconds since 1970. And so for those of you who remember, maybe we had a practice problem on this. There's this NIST group in Colorado that has some pretty cool stuff for figuring out what time it is all the time. And many people in the world rely on them to figure out what time it is. Most of our browsers and our computers and our phones are directly or indirectly tied to NIST. So the number of seconds since 1970 is just the point at which they started counting forward, right? When computers became, ubiquitous enough, they realized this is what we got to do, okay? So if we do something here that takes a lot of time and then we check the time again and subtract the initial number of seconds, that gives us the how long our code took to execute, right? So this is a classic way of measuring performance in code. And sometimes it's really hard to come up with something that takes a lot of seconds, right? We got to really come up with some tricky maths or do a lot of loops to actually come up with anything measurable, okay? So this practice one, and we'll go over this one pretty quick too, but we're going to do 10,000 iterations, but even that's not enough to actually really slow down the computer, so to speak. So we're going to do some square roots. Square roots are classically slow, right, compared to addition and division. They actually take a good deal of time. So if you do anything with that, then you actually end up eating up a lot of cycles. There's a lot of math papers and algorithms that try to figure out ways to factor out square roots in equations to actually make calculations go faster. There's a lot of video game algorithms that try to get square roots out of the calculation so that your video games can go faster. Okay. So here's me creating a very large number or a somewhat large number, figuring out how many seconds since 1970. We kind of think of that as the current time. And then doing something really, really, really intense, right? Calculating the square root over and over and over and over and over again, right? And assigning it to something else just for the fun of it, right? And then printing that thing out. So if you do that, you can kind of see the duration of that. And notice that we're just subtracting the start time from now. That's kind of, think of that as now, right? So now minus start time. And what's interesting is if you compare the time on program IZ to the execution time on Replit, they are shockingly similar, but they are not the same. They're pretty much 3 seconds, but they differ by, microseconds, right? So it's kind of like, who's using the faster computer, right? So notice we're not really measuring the upload and download time or the internet lag because the measurement happens between here and between here. So probably, I think I was looking at it today, I think Program IZ probably has given us a bit of a beefier computer on our servers than we're getting from Replit, okay? And that stuff can be kind of dynamic, so maybe those servers are kind of changing over time, but it's kind of an interesting way of peeking behind the curtain a little bit. Okay, but we'll use time in this class. And again, 0 is just a way of saying, hey, what time is it right now? How many seconds since 1970? Okay, and that's kind of like the easiest way to do, delta, time. But there are other libraries for figuring out the date and the time and the time code and all that stuff, but we'll kind of stay away from that. We're going to use randomness in this class. Random comes from the CST library. Again, sometimes it's preloaded, but if it doesn't work, we got to load that thing up. So just remember that the time null gives us the number of seconds since 1970. And if we feed that into the seed for the random number generator, it's kind of like shuffling a deck of cards every time in a different way. Because as time marches forward, every time you run your program, we're feeding in a larger and a larger seed number because time has marched forward. So this is a trick we've used before to ensure that our game, for example, if we implement risk and we want to roll the dice, we don't want the game to be the same every time we play it. So we want a different seed for our random number generator. And so this is like shuffling the deck in Vegas. Now, if I put a very specific number in there, now I have shuffled the deck in a very tricky way that will guarantee that I will have the same game every time. So this trick of using time null is just a way of ensuring that we're shuffling the deck differently every time we run our program. A lot of times you'll see me when we're giving you a lab, I'll say, okay, let's all use the same seed so that we all get the same result. And I'll tell you the result should be 50, right? And that'll be because I know what the result is going to be because I've kind of stacked the deck. I've said, hey, we're going to all shuffle our deck the exact same way. So you probably saw this in the past. It's just a very powerful way to have a different experience, or if you want to have the exact same experience, we can kind of put a specific number in there. Now, whenever we use rand, which is just one common random number generator, it's going to give us a very large number between 0 and some, multiples of millions. So we're going to chop that down using modulo, and hopefully we all remember modulo. It gives us the remainder. So rand modulo 5 gives us something between 0 and 4 because it's a remainder. We're never going to have a remainder of 5 when we divide by 5, right? So if we want it to be between 1 and 5, hopefully everybody can kind of see by adding 1 to this result, we're shifting the range of that value up by 1, okay? So when we do our dice for risk or something like that, we're going to kind of tweak this equation a little bit to shift the range of the randomness that comes out of it, okay? Yes? Well, rand is a uniform random number generator, and it's not a super, super high quality random number generator. There are some other libraries out there that do a better job than rand does. So yeah, you would never want to build your cryptography library or a gambling game in Vegas based on rand, right? Because someone could probably crack it and figure out what the sequence is. Yeah. So yeah, if you're anybody curious about cryptography, if you ever heard about it, randomness is a huge thing. Prime numbers is a huge thing. So yeah, random number generation is an entire research area all in itself because computers aren't very good at generating truly random numbers. And if your random number generator isn't truly random, somebody can hack it and kind of figure out how to beat the game, right? So if you knew every roll of the dice in order, obviously you'd be able to kind of predict the next move. So being truly random is an important thing. Okay? So just remember that whenever we mod by 5, we're going to have 0 through 4, and that'll kind of help you on your way. I know modulo is a little bit of a strange thing, but it's super powerful for the kinds of things we want to use. Okay. So just quickly, briefly overlooking, we won't look at a lot of these, but RAND and SRAND come from here. But those of you that took algorithms, hey, look, we don't have to write quicksort anymore, right? So quicksort we wrote in algorithms comp 220, but it's in the CSTLib library. So if you all remember what that is, you can actually use that. And there's some other stuff in here like absolute value, but we won't go through a lot of these things right now. Some of you may eventually come back to find these, but there's just a couple of handy things in there that we need from time to time. Okay, so we'll kind of breeze over the top of this one just so we don't kind of put everybody to sleep. But basically, this is about just playing around with that modulo, playing around with your seeding to kind of see what happens. And if you run these things, you should see, and let me just click into our kind of solution here so you can kind of see. So we're going to go from 0 to 10, pick a random number, and then we're going to print that thing out, right? And so my seed is set as my time, right? So I'm saying take the time, put it in there, and so I should get a different experience every single time. So if I run this, now notice with Program IZ, sometimes it's blank. Don't panic, you just got to refresh and rerun it, right? So here I'm going to modulo that huge number by 50. So that means the biggest number I should get should be 49, okay? So if we look at this, we're getting different results every time, okay? And if I, instead of using the random seed, put 1, 2, 3 in there, my results are never going to change, okay? 43, 13, 23, okay? So I'm shuffling the deck in a very specific way and it's never changing, right? If I go back to my time, then we have true randomness, okay? So I know it's a little bit strange, important thing to kind of understand because it's going to allow us to kind of make some more interesting games, okay? Okay, reviewing our ternary operator, just a really nice way to compress a lot of code in a small space. It's always okay to use if else, but if I have a value that's true, I can test it and I can say cout x is, and this whole thing right here is of course just an if else statement. If x is equal to true, question mark, do this. Otherwise, colon, do that, okay? So it's like a little mini function where we're either returning this or we're returning this based on this test right here, okay? So this is the true part and this is the false part always, okay? So we ask a question and then we return a value, right? So that gets you out a lot of tight spots without having to write all that extra code, okay? And if you remember, if we just print out X, we're going to see 0 or 1, even though it's a true false, okay? So Booleans are not integers, so don't be fooled. If you print out the X and it prints a 0, that doesn't mean it's 0. That means it's false, okay? So don't let that throw you. That can create some nasty bugs if you kind of treat it like an integer, okay? Okay. Marching through there then, so we'll let you play around with that, but you can kind of see what happens if you kind of print out whether something is even or odd, right, in a very concise way, okay? So that's kind of the benefit of having that stuff. Always break it down into 3 parts, the question, the true, and the false, okay? Separated by the question and the colon. Gotta have the parentheses in there when you do that, okay? Okay, so that's our ternary operator. All right, let's talk about a few cin tricks because we're going to be reading in information from the command line from our users, or not the command line, but from the input stream. Okay, so we do IOStream, we set the type, and that tells the cin what we're looking for based on the type. Okay, so if I try to load something into an integer, it's going to keep reading until it runs out of numbers. If I try, or it hits a space, if I try to read a character, it's just going to read in 1 character no matter what, okay? So if I say, please enter an integer, a space, and then a character, that's going to work in that scenario. So that means that if the user follows our instructions properly and types a bunch of values, integer values, and then a space, this will read those and then stop at the space, okay? And then the next thing that it will do is eat the character, okay? So it will eat the integers and eat the space, and then it will load the character in. And sort of kind of does what you would expect it to do. It allows the user to do exactly that. Type in some number, give me a space, and then a character. If you put a comma in there, that wouldn't work. You would need CNX, and then you'd have to eat the comma somehow, and then you'd have to eat the character that we want our user to type in. So you gotta kind of set the type on this and hope your user is going to more or less follow instructions. So there's a lot of code we need to write if we assume that we have hostile users. But in this class, we're going to assume that most users are well behaved. But we would have to write a good deal more code out in the real world to kind of keep them from crashing or hacking into our code. Okay. So if you want to practice that, you can. A lot of times when we do text-based games, we want the user to give us lots of things all at once. Like if it's a chess game, you want to say, okay, move, from this location to this location all in one line and just hit enter. So that's going to require this kind of CN understanding to understand how to parse those command lines. And we'll remind you when we get closer to that kind of input stuff. But just remember that you can do multiple inputs on the same line that way. It can save you a lot of trouble, especially in a while loop. So, and we'll do a few patterns like that, okay? So that's our CN, right? And so that will kind of close us out there, right? So it's just kind of nice to be able to, thought that was oh, there it is, right? Yeah, we load in the max value, and then we use that for our modulo. So this is a little bit contrived, but we're just trying to incorporate that CN into our random thing that we did before, okay? So those are kind of our main things, right? And I think what we're going to do now, we're a little bit early, which is great because I don't want to kind of blow you guys up on this review thing. But let's take a look at our lab, which is a little bit tricky, but not too bad. You can definitely knock this one out if you take the easier path. So we're going to have a prototype. So remember that we always put prototypes at the top of our main.cpp, and that's like our blueprints. We don't want to change the prototype, but that tells us what we got to write below main. We're going to write a rotate array where we're going to receive an array of 8 by 8, and our function is going to modify that two-dimensional array. And notice it doesn't have a return value. That's because arrays are passed by reference. That means the function is allowed to modify the stuff inside of the array. It does not need to return the array. So that's our job. We want to try to rotate this 2D array clockwise by 90 degrees. So in our main section, if this is our kind of two-dimensional array, remember that we have these individual rows separated by commas, right? Row 0, row 1. Remember, we always start counting from 0 on the row and 0 on the columns. So notice my purple and my orange. So when we rotate this thing, we want it to end up like that, okay? We'll go through 3 approaches, so you don't have to kind of do this cold. But you're going to end up putting something like this below main and then filling in some information. Notice that this dimension is optional, okay? But we can leave it in if we want, right? So feel free to put the 8 in there if you want. It's perfectly fine. That's really all we're going to be working with is a square 8 by 8 two-dimensional array here, okay? So let's think about strategies for doing this. So we can change it, but it's going to be easier to sort of copy it into some temporary memory and kind of do the rotation while we're doing the copying. That's probably a little more straightforward. But we could find a tricky way to do it without needing any extra memory at all, but that's a little tougher. So let's look at 3 different approaches to doing this. And you can pick any one you want or come up with a new one. But here's our prototype, right? So one strategy is just to create a identical 8 by 8 array internally and copy information from the 8x8 array argument. And in the process of copying it, you're going to swap the rows and columns. Okay. And that is going to essentially do the rotation for us, and then copy that back. So you'll have to figure out how your loop's going to do that as you're going across the row, reading from the original one. You're going to go down the far right column and copy it into that second array. And then you got to copy it back to the original array before you leave the function. So that's probably the most straightforward way to do that. So here's a visualization of that, right? So we go across the top row here, copying it down the side column, okay? And then as we come down from 0 to 1, we got to work our way backwards from the far right column, etc. Okay? So just sort of exercises our memory of how to work with rows and columns, and then just copy it back however you want, okay? So a couple for loops, kind of, one for loop for moving it to temp and one for loop for moving it back, okay? And you may find other ways that you want to do this or some variation on that, but that's kind of our most straightforward approach. So that requires that you allocate this inside of your function, and then it, of course, goes away after the end of your function, but we do end up needing extra memory to do that, okay? So here's another way we can do this, a little trickier, a little harder, is we're going to use a double nested for loop, okay? And we're going to have a temporary integer, and we're going to flip the array from top to bottom by swapping the top row with the bottom row and then moving inward, right? And swapping the next to the top row with the next to the bottom row, one value at a time as we go across the rows. So that's only half the problem, but that essentially inverts our numbers top to bottom. It's like a vertical flip. And then this is a little bit mathy, but if we transpose the matrix along the diagonal by swapping values along the diagonal, then we achieve our 90-degree rotation. Okay, so this is just a slightly sort of visualization test to sort of see how we do this. So here's like the middle line, right? So we would have to like swap these two things, right? Through one for loop, right? And then we kind of move inward. So we're going to have an outer loop that controls, how much inward we moved, and an inner loop that moves across the columns, right? And once we've done that, the slightly trickier part is swapping the lower left with the upper right and realizing that if it's on the diagonal, you don't really need to swap anything, right? So we can just kind of go through and do that. And now we got another modification to our loop, a little tricky there. And then we get our fully rotated thing, okay? So that one, we really only needed one extra integer in order to do that full transformation, okay? So that's kind of nice. Okay, we didn't use a lot of extra space for that. The last one's pretty darn tricky. So anybody looking for a good challenge, right? And please don't use the swap function in all these. It'll mess you up something terrible. We've had some nasty bugs in this class. We'll come back and explain why, but you don't want to use the swap function. So in this one, we're going to use a double loop, and we're going to work in the rings from the outside to the inner ring, okay? And the idea is, we'll show you in a second, we're just going to swap the corners, and then we're going to slowly move across the row and down the sides and swap what's next to the corner. So it's like musical chairs. And in this case, we only need one integer, and we can do it in one pass. So this is probably the most optimal way to actually do this. So I'll show you this here in a picture in just a second. This one's a little tricky. Whoops. Oh, I don't have a picture for that. Oh well, sorry. That's not intentional, I swear. I really thought I did. So again, the idea is, I'll see if I can draw a picture. So if I have our 8x8 thing, imagine that we have our corners here, right? So, and I have a temporary variable over here. So if I move this guy over here, then I can move this one to there, and this one to there, and this one to there, and then this one can go there, and now my corners are done. And now I move over by one, and I play the same game with these guys, right? So I'm going to work my way over slowly as if they were the corners. And once I finish the whole outer ring, I move to the next inner ring and repeat the game, okay? So that is probably the most optimal way to do it, but it's some pretty tight for loop management in there and requires a bit of visualization. So I'll leave you with those 3 options. That's our lab for tonight. Let me know if you have any questions. I'll come around, but otherwise I'll see you on Tuesday and we will start talking about our group project and remind you about homework again, okay? Thanks, everybody. Let me know if you need anything. Otherwise, I'll see you on Tuesday. Okay, bye. Yes.
I didn't know it.